Okay, so now you're going to continue analyzing what you just did in problems 21, 22, and 23 with the next set of questions here. So on your own, I want you to answer 24, 25, 26, 27, and 28. Pause the video to do so, come back and we'll discuss. Okay, so here we're really making comparisons among, which is why I said we're going back and analyzing 21, 22, and 23. So in 24 and 25, we're seeing what happens when you put more resistors in the circuit. So here's our original circuit, problem 21, with just a single 6 ohm resistor. And then 22, we put another resistor in series with the 6 ohm resistor. So really we're comparing the circuit in problem 22 to the original circuit in problem 21. So we put more resistors in series. What happens to total current? Well, we clearly see this current went from 2 amps to 1.5 amps. It clearly decreases. I mean, it's so simple. It makes perfect sense. The REQ increased. So for the same voltage, larger REQ, smaller current. But here the math, of course, shows it. For 25, now we're putting them in parallel. So I just replace this with problem 23. Here's the original 6 ohm resistor. Here's that same 6 ohm resistor with now an extra 2 ohm resistor in parallel. So we put more resistors in parallel. What happened to total current? So the total current went from 2 amps to 8 amps. It clearly increases. I mean, makes perfect sense. We went back to that ski resort analogy. We said when we open up more and more trails, more and more skiers can go. More skiers moving, that's a larger flow. That's a larger current, right? We talked about in terms of resistance, but now we're just talking about in terms of current. Or look at this. Here's the 6 ohm resistor. Here's that same 6 ohm resistor doing the exact same stuff, right? It still drops all 12 volts. It still has 2 amps of current going through. When we put another 2 ohm resistor in parallel with it, nothing changes about this. This is what we mean by when we say that resistors in parallel are independent. Whether this 2 ohm resistor is here or not, this 6 ohm resistor will do its job just the same as if it were all by itself. Just the fact that now we put another resistor there means more charges can flow, whereas originally it was just 2 amps, now it's another branch, another 6 amps can flow for a total of 8 amps. This makes sense. Let's look at 26. For the series in parallel, I want to compare the total power dissipated to resistors, and the resistors to the power output of the battery. So here's our results in 22 and 23. Here are the individual resistor powers. Here's the total power. Here's the total power. It should be very, very obvious. Oh, I'm sure you saw it, that clearly the total power is the summation of P1 plus P2. I mean, that makes sense. And it doesn't matter if it's in series or parallel. I'm not going to make this new equation. It's a good relationship to know that it just provides one more tool in your tool belt for solving the problems. It's one more check to see if things are going well. But whatever power is generated by the source of voltage must be dissipated by the resistors. Doesn't matter if they're in series or parallel. The energy, which remember that's what power is, energy per time. Energy doesn't care where the resistors are or what arrangement they're in. Just energy is energy. So yeah, these two up, we get this. We get these two up, we get this. Easy. Let's look at 27, 28. Now we're looking again, comparing circuits, comparing 22 and 23 back to 21. So first we're putting them in series. So here are two circuits. Here's the 21, the original 6 ohm resistor. Here's 22, put in series with the 2 ohm. Look at the total power. Well, here's 24, here's 18. What happens? Decreases. That's literally all we're doing. We're just comparing. For 28, now we're talking about what happens when they're in parallel. So now we just place this here. Here's the total power. Here's the total power. What happens? Increases. Simple. Okay. Now, why does it increase? So now look at the individual powers. Here's the 6 ohm resistor by itself, dissipating 24 watts. Here's the 6 ohm resistor still dissipating 24 watts. Because remember, that's the idea. And when they're in parallel, they're completely independent. This 6 ohm resistor will do the exact same stuff it did before, whether or not this 2 ohm resistor is there. Just the fact now there's a 2 ohm resistor there as well, more power is going to be dissipated because there's now 72 watts in addition to 24 watts, making a total power output of 96 watts. This has to be. This makes perfect sense. Now, if these were light bulbs, remember, light bulbs' power is really about their brightness. So this is going to be the same brightness as it was before, but now there's a second light bulb making the total output brighter than before. Okay. In series, they were actually dimmer. That's kind of interesting. So let's look at that in a little more detail. Okay, so here are the two circuits, 22 and 23, with a 6 and 2 ohm resistor, here in series, here in parallel. These are the same resistors. Let's again imagine they are light bulbs. The defining characteristic of a resistor is its resistance. And so this is a 6 ohm light bulb, there's a 6 ohm light bulb, there's a 2 ohm light bulb, there's a 2 ohm light bulb, but when they're in series or parallel, their brightnesses will actually differ. So here's the 6 ohm light bulb giving off 13.5 watts. Here it is in parallel, it's giving off 24. It's clearly brighter here, right? Here's the 2 ohm light bulb, giving off 4.5 watts, and now in parallel, oh my goodness, look at that increase. It's now burning at 72 watts, giving off 72 joules per second. And so in general, we see that in series, the same light bulbs are relatively dimmer, whereas in parallel, these same light bulbs are relatively brighter. Let's go back to our chart to compare series and parallel. We'll add one more bullet point, that in general, when light bulbs are in series, they're generally dimmer, and when they're in parallel, they're generally brighter. For the same two light bulbs, or the same, that's only two, but the same light bulbs attached to the same voltage source. That's really what we're looking for, right? And of course, you saw this in the original PhET simulation. When you put the light bulbs in series or parallel, we wrote this down on the first circuit's activity. They're in series, they're dim, when they're in parallel, they're bright. Feel free to look back at that and verify that's exactly what you saw, or build the circuits again in the PhET simulation. It's up to you how you'd like to see it.